Hi, this is Professor Pradyot from Leadib Academy, one of the leading institutes which provides the coaching for IB diploma. Okay. So we are basically looking into this IBDP Chemistry HL Paper 2 May 2019, okay, video solutions. But interestingly, these are not just the solutions, but I'm explaining even the underlying concepts, okay? So that it is more like a quick revision, okay, for getting those underlying concepts. So it will be much interesting, okay? And besides that, interestingly, Leadib Academy provides the courses, okay, for chemistry, physics, math for IB diploma. So please do visit our website, okay, where we are uploaded our courses. So you can subscribe to them. Anyways, now let's look into this interesting question. Okay, 3A1. The question is being asked, dinitrogen monoxide causes depletion of ozone layer, okay, in the stratosphere. Outline why ozone in the stratosphere is important. Okay, so let me just explain, okay, very simple way so that you people will get the idea. Okay, so first of all, understand that when we say, okay, the first of all important part is that ozone layer, okay, takes care of, or it fights, okay, prevents harmful UV radiations reaching the Earth's surface. Okay, this is the important reason. Now let's understand that in case of UV radiation, when we say UV, that is the ultraviolet, and you know that ultraviolet means these are high energy radiations. Okay, high energy electromagnetic radiations. But in that, there are three categories: C, ultraviolet C, B, and A. Now, the highest energy is in the ultraviolet C. Okay. Fortunately, the oxygen in the stratosphere takes care of this. This is being taken care by oxygen. Okay. So, poor oxygen will get split into these two oxygen free radicals, while ultraviolet B is being taken care. Okay, now understand that C is the highest energy, okay, highest energy amongst ultraviolet, followed by B. The reason being that oxygen is a double bonded, so you require higher energy to split, while in case of ozone, okay, we know that it is basically a resonating structure. Okay, let me be clear. This is like a resonating structure of ozone. So it is like 1.5 bond. So obviously it requires a less energy as compared to oxygen double bonded. So again, poor ozone sacrifices and it will basically undergo decomposition and it will produce, as a matter of fact, it is producing oxygen. It sacrifices itself and produces oxygen and one free radical. So the only radiations, ultraviolet radiations, which are reaching the Earth's surface are A, which are less energy, less harmful. Okay, we'll say less harmful. So the ozone layer, which first of all, ozone is in the very small quantity. Okay, maybe in the ppm level. Okay, it's in the ppm level, and that itself, if it get destroyed, then all these UVB also will reach Earth's surface, which are harmful. Okay, because anyway oxygen is taking care of the highest energy, but the problem is with the UVB mainly. So that's the importance of the ozone layer. Okay, hope this is quite clear. Let's look into the question number 3A2. Dinitrogen monoxide in the stratosphere is converted into nitrogen monoxide gas. Write two equations to show NO gas catalyzes the decomposition of ozone. First of all, okay, let's look into this. Nitrogen monoxide. So what is the specialty of nitrogen monoxide? It is having odd electrons. Okay, it is having odd electrons because typically it is in the pairs like 2, 4, etc. But in case of nitrogen monoxide, there are the odd electrons. Okay, and that's why it is highly reactive. Okay, so let's look into this reaction. So here comes NO. Ozone is in the gaseous state and it converts into nitrogen dioxide, NO2 gas, plus oxygen. Okay, and the second part, that this nitrogen dioxide which is getting formed, okay, can be converted, okay, can convert this ozone into twice oxygen. Okay, now interestingly, what do you see? The real interesting part is this, that NO, which took part in the first step, has been regenerated back. Okay, this has been regenerated. It means that it will keep on destroying the ozone because poor ozone is getting destroyed. Okay, and we have already seen what is the importance of the ozone layer, because it prevents UVB, okay, high energy radiations. Okay, so that's the problem. Okay, so we will say in above reactions, so this is one reaction number 1, reaction number 2, and important is that in the above reaction, NO is getting regenerated. Okay, and therefore NO is acting like a catalyst because it is not getting consumed at all. Okay, that's the issue. Okay. So hope this is quite clear. So these are the two reactions. An important part to be understood, that nitrogen monoxide is acting like a catalyst because it is getting regenerated in the step 2. It is not getting consumed. Okay. So very, very straightforward. Okay, question number 3B1. Different sources of N2O, okay, dinitrogen oxide, have different ratios, N14 to N15. State one analytical technique that could be used to determine the ratio, okay, of N14 to N15. Simple. We know very, very powerful technique that is called a mass spectrometry. So in mass spectrometry, okay, what happens, that important part, that it sorts out the particles according to mass to charge ratio. Simple. Okay. So this is the technique in which mass to charge ratio. So in this case, N14 and N15, we can clearly see the difference is between the atomic mass. Okay. So mass spectrometry or mass spectrometer will be helpful, okay, in sorting out this, okay, to determine the ratio. Very, very simple technique. Okay. Hope this is quite clear. Okay, 3B2. A sample of gas was enriched to contain 2% by mass of N15 with the remainder being N14. Calculate the relative molecular mass of resulting N2O. Simple. So what we should do now? The first thing, very, very important, calculate relative atomic mass of nitrogen. Why? Simple, because there are two isotopes. Which are those? Okay, there is a N15 and N14. So N15 is 2%. So I'll say N15 2 multiplied by 15 plus 98% of 14, and then we divide by 100. So we will get 14.02. Okay, this is the relative atomic mass of nitrogen. Okay, normally we would have taken just 14, but in this case they are specifically mentioning about two isotopes, okay, N14 and N15. That's the reason. Now they are asking us to calculate relative molecular mass of the resulting N2O. Simple. So let's calculate. Same technique, relative molecular mass of N2O. So what we'll do now, in case of N2O, okay, how we calculate, there are two nitrogens and individually the nitrogens relative atomic mass is 14.02, and then there is one of oxygen. We'll refer to the data booklet, and we are aware of that it is 16.00. That's all. Okay, so it works out to be 44.04. Simple. Okay, very, very straightforward. The important part is this, that don't use directly the 14 alone, because the nitrogen is consisting of two isotopes, N14 and N15. N14 98%, that's the reason. Okay, this is the percentage of N14, and this is the percentage for N15. Okay, and therefore we got this relative atomic mass. Okay, very, very straightforward. Okay, let's look into the question number 3B2. Predict, giving two reasons, how the first ionization energy of N15 compares with that of N14. So first of all, we should be looking into what do you mean by first ionization energy. I'm writing in short IE. What it means. The ionization energy, first ionization means it's a minimum amount of energy required to remove one electron from the gaseous atom. So let's analyze with this definition. What does it mean? That means, let's say there is a N14. So obviously, what will be the nucleus? So it will have plus 7 protons, and there are going to be 7 neutrons, which are neutral. And outside, obviously, there are going to be, I'm just showing like this, there are going to be 7 negatively charged electrons. Okay, this is for N14 scenario. Now let's compare it with N15. So N15, the protons cannot change because it's an isotope. What is going to change are the neutrons, 8 neutrons. And what about the electrons? So electrons are identical, -7. So please note that it doesn't matter how many neutrons are there, whether it is 8 neutrons, 7 neutrons, 5 neutrons, it doesn't matter in terms of the attraction, because the force of attraction is between these positively charged protons, which are there inside the nucleus, and outside 7 electrons. Okay. So in case of both this one, that is identical. Okay. So please note, so the first reason, okay, that IE depends, okay, only on nuclear charge and not on number of neutrons. And second reason, in case of N14 and N15, nuclear charge remains same. Straightforward. Okay, it should be very clear that in case of both N14 and N15, these are the isotopes. So in case of isotopes, the number of protons and electrons do not change. The only difference is the number of neutrons inside the nucleus. And neutrons being neutral, they do not play any role in terms of the attraction. Okay, so first understand what is mean by ionization energy. That is the minimum energy to remove electron. And why you need energy to remove electron? Because there is an attraction from the nucleus, nuclear charge, that is attracting those electrons. So if that is not changing, then why IE should change? Simple. There's no reason why IE should change. Simple. Okay, so it's very, very simple. These are the two reasons. Hope this is quite clear. Okay, let's look into the question number 3C. Very interesting one. Explain why the first ionization energy of nitrogen is greater than both carbon and oxygen. So what is the best tool available to us is the electron configuration. Please remember, electron configuration helps us a lot, okay, in majority of the time. So in case of nitrogen, it is 1s2, 2s2, and more interestingly, 2p3. That means all it is, okay, the p orbital is completely half filled. Okay, not the right way, but we'll say half filled orbital. Okay, there is one singly paired electron, okay, not paired, single electron in each p orbital. Now coming to the carbon, 1s2, 2s2, and obviously there are only 2 electrons, okay, in the p orbital. While in case of oxygen, 1s2, 2s2, 2p4, that means in one of the p orbitals, the electrons are paired up. Now let's start comparing it. Let's compare nitrogen and carbon. Simple. We are trying to remove electron from one of the orbital. Okay, outermost electron, not one of the orbital. Okay, one of the p orbitals. So, which is having a higher nuclear charge? Simple. Nitrogen is having 7 protons. So it is exerting much more higher attraction on these electrons, okay, as compared to carbon, because carbon is having only 6 protons. So the force of attraction on the individual electron is going to be less. So we will say, in case of this, higher nuclear charge is playing a role in nitrogen. But finally, everything revolves around how nucleus is exerting a force on the electron which need to be removed. What are the factors? Simple. So obviously there are 6 protons only in case of carbon as compared to 7 protons in nitrogen. So obviously the force of attraction will be higher for nitrogen as compared to carbon. Okay, that tells the story for this. Now coming to the more interesting one, okay, between nitrogen and oxygen, because we are then we can say that oxygen, in case of oxygen, 8 protons as compared to only 7 protons in nitrogen. So by applying that logic, oxygen should have more ionization energy. That means it should be more difficult to remove one of the electron. Now comes the tricky part. Okay, not the tricky part, but interesting part. That please remember that in case of oxygen, it is not half filled, but in one p orbital, there is a pairing up. Now what is the effect? Pairing up in the same p orbital, there are 2 electrons which are staying close to each other. They have been paired up. So obviously there is going to be a repulsion. Okay, there is going to be repulsion between these 2 electrons because both are negatively charged. Even though they are paired up, okay, but still there is going to be a repulsion. So it will be much easier to remove this electron as compared to any of these electrons. Simple. Okay, so we will say the reason is pairing of electrons in one of the p orbitals. And as we know, we have seen many times, okay, the half filled gets extra stability. Half filled and completely filled orbital always get extra stability. So this is the very important aspect. Okay, nitrogen and carbon quite straightforward, but in case of nitrogen and oxygen, you need to be very clear that half filled one give extra stability. In case of oxygen, one of them is paired, so there is going to be a repulsion, and so it would be easier as compared to nitrogen. Simple. Okay, stick to your basic fundamental, and we have covered all these deeper concepts in detail in our courses. Okay, so please do visit and okay our website, that is Leadib Academy, and we have basically you can subscribe to those courses. Okay, so please do visit. Okay, next question. So what the question number 3D1. The Lewis structure, electron dot structure of dinitrogen monoxide can be represented like this. So they are showing basically two structures. Okay, this is structure number 1 and this is structure number 2. So the question is, state what the presence of alternative Lewis structures show about the nature of bonding in the molecules. Okay. So first of all, let's understand what is being done here. Okay. So there is nitrogen triple bond. I'm purposely showing with the different color. Sorry. Okay. And then another nitrogen, and then oxygen. Okay. Lone pairs, lone pair. Okay. Now, in case of this, what is happening? Understand it very, very clearly, very simple. So, what is going to happen that one of the pi bonded electrons are going to shift to this nitrogen, okay? And one of the lone pairs on oxygen is going to get shifted here. So what is going to be the impact? Okay. So the impact is straightforward, that nitrogen, okay, has got now, it has got, because this is pi bond, that means 2 electrons. So it has got now 2 extra electrons. So let me show it with some different color. Okay. And now it has got only 2 bonds. Okay. Only 2 bonds. While here, between nitrogen and oxygen, so whatever the 2 electrons lone pair which has come, it is going to form a new basically bond, and we will get what I had done, oxygen, and like this. Okay, this continues to have this. Now it has the negative charge has shifted here. Okay, while here earlier the negative charge was here. Okay, so basically there is a delocalization of electrons. Okay, delocalization of electrons, and that concept we call it as a resonance. Now if we have been asked, okay, let's number this. This is number 1 nitrogen, this is second number nitrogen, and oxygen is as it is. Now if we have been asked that what is the exact bond between 2 nitrogens, is it a triple bond or is it a double bond? And the answer is none of them. Okay, it will be either, so it just keeps on moving. Okay, that's the concept. So what we can say that while drawing the structure, we will draw like this. 1, okay, and same here. Okay, and the third bond, I'm just showing it like this. Okay, and plus charge continues to be here, while these nitrogen and oxygen, they are basically sharing this minus charge. So this is what we call a resonance or resonating hybrid. This is the hybrid structure. Okay. So this actually what we should understand. So because of the delocalization, there is a resonance, which is resonating structure, which is being formed. So there is neither double bond nor triple bond between two nitrogens. We can think for all practical purpose, it is like 2.5 bond. Okay. And similarly between nitrogen and oxygen, it is neither single nor double. So it is like a 1.5 bond. Okay. This is the idea. And there is a delocalization. That means electron, lone pairs and pi bonded electrons, they keep on moving. They are not stationary. Okay. So this basically is the implication of these two structures. Whenever there are alternative structures, that means we are referring to the resonance concept. Extremely simple logic. Okay, 3D2. State giving a reason the shape of the dinitrogen oxide molecule. So we can pick up any of these structures. Okay, so let me try to draw. I'm purposely writing like this. Okay, with the different color for a sigma bond. Let me, I think, then show the color for the sigma in orange. Okay, and then let me show the lone pair plus oxygen, 3 lone pairs and minus. Okay, I'm picking only one of the structures, and we are trying to derive the geometry or shape. So let's focus as usual how we determine the shape. So our focus is on the central atom, Ca. Nitrogen is the central atom. So first we will find out how many bond pairs are there. That means we are talking about the sigma bonds. So clearly we can see on Ca central atom, that is nitrogen, there are 2 sigma bonds. And how many lone pairs? There is no question of lone pair because it is already plus charge. That means it is a deficient for electrons. Okay, electron deficient. So no lone pairs. Okay, 2 sigma bonds or 2 bond pairs. So total electron domains is equal to 2. And we know very well, okay, if there are 2 electron domains, then the shape is linear. Okay, very straightforward. Find out the electron domains. Electron domains are nothing but the bond pairs plus the lone pairs. In case of this, lone pair is 0. Okay, there is no lone pair at all. As a matter of fact, it's an electron deficient. So total number of electron domains are 2. So the shape is linear. Simple. Okay. Question number 3D3. Deduce the hybridization of the central nitrogen atom in the molecule. It means they are asking us about this. Very, very simple. This nitrogen is triple bonded. It's triple bonded. Therefore, sp hybridize. If it would have been single bonded, okay, always remember this. Single bond sp3, only double bond, one single double bond sp2, and triple bond sp. Okay, quite simple. Okay, so if you want to have a detailed understanding and explanation on this concept of hybridization, please do refer and subscribe our courses. We at Leadib Academy have uploaded the courses for chemistry, physics, and maths. So please do visit.